All right, welcome back. We're going to do sections 2.5 and 2.6, talking about, first of all, talking about measures of center of the data. So the measure of center is a value in the center or the middle of the data set, and we have three of them, actually: mean, median, and mode. You've heard of these, hopefully. There they are, mean, median, and mode. So first of all, mode is the simplest. It's the value that occurs with the greatest frequency in the data set. A data set can have no mode, no value repeated, or several modes. It's bimodal when two data values occur with the same frequency, and it's multimodal when more than two values occur with the same frequency. So just keep in mind, it's the most frequent one you see, and it's possible that it doesn't have a mode. Now, arithmetic mean, there we go, is the average value of a data set found by adding the data values and dividing by the total number. This is the average you've done since, elementary school. This is what you're familiar with. So there's some symbols you need to be aware of because of the way the formulas will be given to you. This sigma right here is the sum of all the datas, okay? X is the variable usually used to represent the individual pieces of data, like grades in a grade book or whatever. N is the number of data values, like how many pieces of data are you adding up. Capital N is the number of data values in the population. So here's the difference. This is population, lowercase is sample. And it is important that you know that because the formulas do differ when we get more complicated here in 2.6 and 7. So as far as mean, finding arithmetic mean, it's really the same. If you look at the formula, X bar, which is the average of a sample, okay, and we pronounce it X bar. We're really fancy, okay? But that refers to a sample mean. Remember, it's a subset of the population. And look, it's the sum of all your values divided by the total number of values in the sample. That's all the simple means, okay? Now, mu, this symbol right here, it looks like a curly M, and we pronounce that mu. That is the population mean, okay? X bar is the sample mean, mu is the population mean. You do have to know those symbols, okay? So notice the difference, the only difference between these two equations is the lowercase n and the uppercase n. And that's because the uppercase n, it represents the population. So just remember, is this value, let's come back to X bar. Is it a statistic or a parameter? Well, hopefully you remember, if it comes from a sample, that means it's a statistic. And on this one, on mu, since it comes from a population, it is a parameter, a summary of a population. Okay? So let's move on. Table 3 represents the first exam scores of 10 students enrolled in a section of intro stats. All right, compute the mean. Easy enough, okay? It's a population mean, so I'm going to use my symbol mu, and the formula says it's the sigma of X over capital N. Okay? And I'm just going to add these puppies up. All right, so I get 82 plus 77 plus 90 plus 71 plus 62 all the way down plus 88. Add those up, and I'm going to divide by 10 because there's 10 of them. When I do that, I get an average score of 79. Okay, pretty simple math. Now it says take a sample from the class by randomly selecting 4 students, so n is equal to 4, then compute the sample mean. So I'm just going to pick 4, all right? So now my symbol is X bar. It's still sigma of all the values I choose divided by n. So which ones do I want to choose? I'm going to choose Ryan, I'm going to choose Dave, I'm going to choose Joel, and I'm going to choose Sam. So there's my 4 people. So I'm going to take 77 plus 68 plus 74 plus 84. Add those up and divide by 4. That gives me an X bar value of 75.75. Okay, but notice I had to take a sample first. Not a big deal. Number 7, the following data represent the monthly cell phone bill for my wife's phone for 6 randomly selected months. Not my wife, but Compute the mean, the median, and the mode monthly cell phone bill. Well, let's to find mean, we have to add them all up, right? Notice it says that this is for 6 randomly selected months. Is this all the months? No. So n is 6. It's not the population, so this is an x bar. And if I take my sum of all my x's and I divide by 6, which is my sample size, if I add those all up and divide by 6, I'm just going to cut to the chase here, I come up with a mean of 41.46. All right? Sum of all 6 divided by 6 gives me this. Now, that's the mean. Now for median, I do need to put these in order from least to greatest. That's the first thing you have to do. So 35.34 is the lowest. Then it goes 38.93, then 39.43, 42.09, 43.39, and 49.36. All right, so 1, 2, 3, 4, 5, 6. That means I don't have a middle, so what do I have to do to find the median? I have to average those two. So I do 39.43 plus 42.09, divide by 2. That's the median. That would give me 40.76. So x bar equals this. This is the median. Remember, a capital M is for median. And then the mode, does this data set have a mode? Well, none of these numbers repeat, so it has none. Easy enough. Now, so we've discussed 2 measures of central tendency. So both of these are considered measures of center, mean and median. Those are the most commonly used, but which one is better? And it all depends. So I'm going to switch the screen and show you some demonstrations. So you have the space to take notes as you wish, but I want you to catch the difference between mean and median and when would be appropriate to use which one. So let me pause real quick. Okay, so what I have here for you is what they call a dot plot, and it's just pieces of data listed least to greatest. Each little dot represents one piece of data. And you can see the distribution of the data. And you can see that it kind of makes a bell curve right in the middle. So at the top of the screen, you also see where it says mean and median. It gives you both measures of center. And if you'll notice, mean is 4.97, median is 4.94. They're very, very, very close. And that is due to the fact of the shape of the distribution. Okay? So if your distribution kind of looks like this as a bell curve, your mean and your median are relatively the same number. Not perfectly exact, but relatively the same. Now, what happens if it's not this shape? So let me show you. If the distribution looks like this, like the data is actually split between the low end and the high end, you still have a mean of 1.95, but the median is 0.96. That is a big enough difference to be significant. So notice that which measure of center would better describe this? Well, where's the majority of the data? The majority of the data is at the low end of the spectrum. So if I really wanted a true center, I would use median because it's more reflective of the actual value. 1.95 is higher than most of these values, so the median is the better measure of center. And here's the reason. All these points way over here are dragging the mean with it. The mean is what we call non-resistant. It cannot resist these points. So if I take one of these points right here, watch what happens to the mean. Did the median change? No, the mean is changing, okay? Every point that I move towards what we call the tail of the distribution is changing my mean. It is non-resistant to the move. All right, and look at the green arrow. It is moving closer to the tail, and so we say the mean chases the tail of the distribution. It is non-resistant. The median, notice, has not changed one bit. Now, what about if it's the other direction? Let me show you. So notice this. This isn't different. It's kind of flipped. There's more data in the high end of the spectrum on numbers than the low, and so our mean and our median do not match up. Notice we have a green and a red arrow, meaning they're not the same. They're not close enough to call the same. So you have to ask yourself, which measure better depicts where all the data is? Well, most of the data is close to 10. Then this data down here that's close to 0. So the best measure of center would be median here. Median is resistant to outliers, it's resistant to pieces of data that don't follow the pattern. So notice what happens if I take a piece of data over here that's on the right and I move it towards the left. Notice which number of center changes. It's the mean that's changing. The median never moves. So the median is what we call non-resistant. The mean is what we call resistant to change. So depending on the shape of the distribution, that determines which measure of center we want. So I'm going to switch back to our note. Okay, so hopefully you made some notes in here going over what I just showed you, and we'll pick up some things here in a minute. But here's what we call, here's the word you need to know, resistant. I mentioned this before. A measure of center is resistant if, or a measure is resistant if extreme values, meaning very large or very small, relative to the rest of the data, do not affect its value substantially. Then the data is said to be resistant. Okay, so we have, right now we have two measures of center. Mean, if you remember from the applet that I was showing you, the mean chases the tail. Okay, it chases the extremes, if you will. That means it is non-resistant. The median is resistant. All right, so if your distribution has a clear tail end to it, you want to use median as your measure of center. If it's bell-shaped, then a mean is fine because they're basically the same number. You want the number that best represents the data set. All right, let's keep looking at this. So why would I ever compute the mean, you ask? Okay, well, the mean and the median are close, very, very close for symmetric data. And the median is both the measure of central tendency for skewed data. That's what we call skewed, and we'll talk more about that word here in a moment. However, much of the statistical inference that we perform is based on the mean. So while it seems like we shouldn't use it because it's so flighty, we still do need to know what the mean is and how to use it. So let's just do another example of mean. So look at example 8. Find the population mean or the sample mean as indicated. So if it's a sample, remember the formula is x bar. It's still the sum of your x's divided by your sample size. So when I do the sum, divide it by 1, 2, 3, 4, 5, I come out with a mean of 11. Population, it's real important that you get your symbols right. Mu is equal to the sigma of all these terms divided by the population size, which is capital N. So it's the same process though. 3 plus 6 plus 10 plus 12 plus 14 divided by 5. I have computed this for us, so it comes out to 82. All right? So here's a question. For Super Bowl 60, CBS Television sold 65 ad slots for a total revenue roughly $162 million. What was the mean price per ad slot? So mean price per ad slot. All you'd have to do is use our formula. Okay, it's the mean per ad slot, so we're talking about all of them. It's the sum of all the ad slots divided by the total, right? Well, we know the total is 65, and we know that it's roughly 126. And when I divide that, I get the mean cost per ad to be $2.5 million. All right, that covers 2.5. Really, it's just measures of center, mean and median. So in 2.6, we're talking about these distributions that I was showing you, and we're actually giving them names here. All right, the shape of the distributions that you need to know. All right, first one is called the bell-shaped, but we also call it the normal distribution. It's that means the highest frequency occurs in the middle, and they kind of taper off on the end. So it's the bell curve that you've seen all around. Okay, bell-shaped. That's great. Now, the right skewed distribution, sometimes they call it right-tailed, is when the tail occurs on the right side, okay? So I always try to think of it this way. Think of it as a whale, and where is his tail? Well, if his tail's on the right, it's a right skewed distribution, Okay, this is what I was kind of trying to mimic in that applet. So you can imagine the creative name of this guy over here, if the tail's on the left, this is a left skewed distribution. Now, what does that even mean? Well, if it's right-tailed, most of the data is lower, but you do have some high extremes. Left skewed would mean I have some low extremes, but most of the data is higher. So, in distributions that are symmetric, the mean and the median are close in value like I showed you. Now, when data are either skewed right or left, there are extreme values in the tail which tend to pull the mean in the direction of the tail. Remember I told you the mean chases the tail. Okay, mean chases the tail. So it's going to move. The mean is the mover. So look at this little diagram. It'll help kind of bring it together. So in example, right skewed distributions, there's a large observations in the right tail. These observations tend to increase the value of the mean, having little effect on the median. So look at this diagram. I know it's kind of blurry, but here's our right skewed, right? So notice the location. The mode is the peak. The mean is here, but the median is higher. So I would say the median is less than the mean. Okay, if you're not sure what I mean by less than, think of this guy right here as a number line. And my numbers are getting bigger and bigger and bigger, and they're getting lowered this direction. Okay, so if the mean is moving right, those values are getting larger. So the median is less than the mean. Okay, so what about if it's left skewed like this? Well, again, think of it as a number line. If my numbers are getting lower down here and they're higher over here, well, how do the mean and the median compare? Well, the mean is lower than the median. Okay, so it's important that you understand, even without an image, that the different skews and which way it pulls the mean and the median. For me, the easiest thing to do is to sketch a drawing and then logic it out. Okay, keep in mind the mean chases the tail of the distribution. If you can remember that, you're going to be good. All right. We'll see you in class.